Hey PCAM, today we're doing section 7.7 notes, which involves calculating equilibrium concentrations. So now we're kind of working backwards. Given an equilibrium constant or value, we should be able to solve for concentrations at equilibrium. So this involves concentrations and partial pressures as well, because remember we can use either value to express the equilibrium constant. And we're going to be doing this using something called ice charts, which are also known as ice tables, rice tables. They go by a lot of names, but they're all essentially the exact same thing. So here we have an example. Suppose you start out with only H2O gas in a rigid container at 25 degrees Celsius, and its initial pressure is 0.784 atmospheres. What are the partial pressures of each species when the system reaches equilibrium? We've been given an equilibrium constant Kp equals 2 times 10 to the negative 42, and a balanced chemical equation, 2H2O gas yields 2H2 plus O2, and that is a reversible reaction, goes both directions, and at equilibrium, they occur at equal rates. So will the partial pressures of H2 and O2 be greater than or less than that of H2O at equilibrium? They're actually going to be much less than H2O because, and I know that because of the Kp value. This Kp value is very, very small, so we know that it favors reactants rather than favoring products. So our first step in solving this problem is to set up an ICE table. ICE stands for initial change in equilibrium. Sometimes you'll also see it shown as a rice table, where the R stands for reaction, where you write out the balanced chemical equation, because the reaction kind of helps you out with this ICE table. And we're going to basically algebraically express what's happening in this reaction. So initially, given by the problem, we start with 0.784 atmospheres of H2O gas. In the beginning, there is no H2 and no O2, so their partial pressures are both going to be 0. For the change, I don't know the number that it's changing, otherwise I would know where it would be at equilibrium. So I'm going to express it with an X value. Since we are going from reactants to products, our reactant is going to have a minus sign in front of it because we're losing reactant. And it's minus 2x, I get 2 from the stoichiometric coefficient in front of H2O. For both of our products, they're going to be a positive change value because we're gaining products as the reaction proceeds. For H2, we have a 2 coefficient, so we have 2x, and for O2, there's just 1, so it's just plus x. Equilibrium, all that we have to do is add these two boxes together to get our equilibrium value expressed algebraically. So for the pressure of H2O, it should be 0.784 minus 2x. For O2, it's 0 plus 2x. Sorry, for H2, it's 0 plus 2x, and for O2, it is 0 plus x, which is 2x and x respectively. The next step is to write the equilibrium expression with the algebraic values that we just found in the equilibrium portion of the ICE table. So here again we have our balanced chemical equation. The equilibrium expression for Kp should be the pressure of H2 squared times the pressure of O2 divided by the pressure of H2O squared, and don't forget those exponents because of the coefficients in the equation. So here if we plug in our values, we have 2x squared times x divided by 0.784 minus 2x squared. And those are just values that were, again, plugged in from the ICE table. We have a Kp value given in the problem of 2.0 times 10 to the negative 42. And then we can use algebra to kind of set up to reduce and simplify the numerator and the denominator. So numerator, 2x squared becomes 4x squared, times x is going to be 4x cubed. And then here at the bottom, there's this note that says when K equilibrium is less than 1 times 10 to the negative 4, usually you can ignore that x value, whatever it is, in the denominator, just to simplify the math and to avoid having to use the quadratic equation to solve for x. So it will usually end up being too small to have an effect on the denominator when you take sig figs into account, okay? So if you imagine x as being very, very small, If we had 0.784 minus 0.00000001, you basically still have 0.784. So that's why we can ignore that, because we're assuming this x value is going to be very, very, very small, and because of sig figs, we can essentially literally just ignore that value. And that can be kind of hard to wrap your head around and accept, but it's going to make your life a lot easier. If it is not very small, if x would have an effect, then we have to use the quadratic equation to solve for x. And that's a lot of work. We haven't, based on the people I've talked to, haven't really seen an AP exam problem where you have to use the quadratic equation, because it does take a really long time to use that. So usually they won't do it. I won't say that they never will. It's a possibility. They say that, you know, it's not guaranteed that they won't. But odds are you will not have to use the quadratic equation and can assume that x is very, 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 very small. Okay. So there we have a simplified equation where we can now solve for x. Okay, so by solving for x, we can find our answers. X is equal to 6.7 times 10 to the negative 15 atmospheres. So for O2, since it is just x, that's literally our answer for the pressure of O2. For H2, remember it's 2x, so we have to do 2 times that value, which gives us a value of 1.3 times 10 to the negative 14 atmospheres. And then we also have to also find the pressure of H2O at equilibrium. So we take 0.784 minus 1.3 times 10 to the negative 14, which again is very, very, very small, so it's basically reported as 0.784 atmospheres. And now we kind of check our answers in two ways. So the first check is making sure that x would have no effect on the pressure of H2O at equilibrium when sig figs are taken into consideration. So since 1.3 times 10 to the negative 14 atmospheres is much less than 0.784 atmospheres, we're okay. It would not decrease the denominator in a considerable way. The second check is to check the Kp value. So the Kp in check 2 is a little smaller than the Kp given in the question. They're very close, so it's fine. Okay, so we have 1.8 times 10 to the negative 2 instead of 2 times 10 to the negative 42, but that is close enough, very, very close in value, so we feel good about those answers. So that's an example that used pressure. Here we have an example that uses concentration. We want to find the equilibrium concentrations of all these species if 0.194 moles of COCl2 is allowed to come to equilibrium in a 5.8 liter container at 25 Celsius. And we're given the Kc value here of 7.27 times 10 to the negative 34. And this again is much less than 1 times 10 to the negative 4, so odds are we can do that thing where we ignore the x expression in the bottom of the denominator of our equilibrium expression. But we're not there yet. So the first step for this problem is that we're not actually given concentration. We are given the moles of COCl2, our reactant, that is present in 5.8 liters. So we're not explicitly given our concentration. So what we're going to have to do is find concentration. To find our concentration, we're taking the 0.194 moles, dividing it by our volume, 5.8 liters, and that gives us a concentration of our reactant of 3.3 times 10 to the negative 10 to the negative 2 molar. So this here is our concentration value. We don't just put in the number of moles, we are actually interested in concentration, so that's why we have to have moles per liter or molarity. The next step is to set up our ice table. So here we're starting with an initial value for COCl2. We just found that concentration. And then the initial values for CO and Cl2 on the product side should both be 0 at first. And then this is, of course, in concentration, molar, moles per liter. Our change we're going to express algebraically. Everything here has a coefficient of 1, so we're going to do minus x for our reactant and then plus x for each of our products. And then at equilibrium, we just express the two boxes, add the two boxes together to express the equilibrium of those concentrations. So we have 3.3 times 10 to the negative 2 minus x, and then 0 plus x and 0 plus x, which both turn out to be x. Next, we set up the equilibrium expression with algebraic values that we just found in our ICE table. So we were given a Kc value, and we know Kc is equal to the concentration of CO times the concentration of Cl2 divided by the concentration of CoCl2. And remember, if these were solids, they wouldn't be expressed in the equilibrium expression. So we plug those in. We have x times x divided by 3.3 times 10 to the negative squared minus x. We don't have anything squared here. And then, of course, when our K equilibrium value is much less than 1 times 10 to the negative 4, we can usually ignore that x, so we're going to go ahead and nix that in our final equation here. Our given Kc value was 7.27 times 10 to the negative 38. X times x is x squared, and then again in the denominator we just have 3.3 times 10 to the negative 2. Now we can plug and chug, solve for x, and we find that x is equal to 4.9 times 10 to the negative 20 molar. Now we go back to that ICE table in the equilibrium section and apply that x. So for both CO and Cl2, those concentrations were equal to x, so they should have a concentration of 4.9 times 10 to the negative 20 molar. For our reactant, it's going to be 3.3 times 10 to the negative 2 minus x, but with sig figs, since this is such a small number, that's basically 3.3 times 10 to the negative 2. And then we go through our two checkpoints. So the first checkpoint, 4.9 times 10 to the negative 20 is much less than 3.3 times 10 to the negative 2. You know, negative 2 is a lot larger / smaller than negative 20. So it should have no effect on CoCl2. And in our second check, we plug the values back in that we found in the beginning, and we get 7.28 times 10 to the negative 38, which we were given 7.27 times 10 to the negative 38, but those values are very close together considering sig figs, so that is an accepted value. We're pretty confident that that is a reasonable answer, okay? So when you do the math, it should, again, give you a value that's close to the K that was given in the problem. It might not be exact, but it should be close. So we were only off by 0.01. That's a pretty good math right there. Okay, let me know if you have any questions. You can start working on the 7.7 worksheet where you will get some practice with these ICE tables, and have a wonderful day.